electric potential. Electric potential. This is related to the electric potential energy, which we'll talk about eventually. But it's a concept, it's sort of a construct that helps us solve problems, okay? And in practice, usually when you're solving these electromagnetism problems or electric field problems, you're going to use this idea of electric potential to solve problems, and then once you find the electric potential in a region, you can easily extract the electric field, and I'm going to eventually show you how to do that, okay? So imagine a uniform, doesn't have to be uniform, let's just say any old field. Here's some electric field, okay? Place a test charge in this field, a little Q naught, it's positive. Q naught, all right? Due to this charge being in that electric field, there is some potential energy, electric potential energy, based on the position of the charge in the field, the strength of the field, okay? And you know that since this is positive, there's some force on this charge being in the electric field. There's some force, and so if it were allowed to move, this thing would take off, okay? There's some potential energy, electric potential energy, based on its position, the size of the charge, the field, all those things, okay? So the electric potential, V, is equal to U over Q naught, where this is the electric potential. So I said it's related to the potential energy, but we're going to see how we don't need energy to solve this or to create this electric potential idea. V is or has units of joules per coulomb. That's called a volt. And the symbol for volts is V. So if electric potential is V, volts is V, everything's V. We'll see how to deal with that. It's really not that confusing. All right? So what we do is we typically are looking at, let me use red for the electric field. We're looking at a change in position in an electric field. No, I changed my mind again. I'm going to draw a uniform electric field. It just makes it easier. Okay, so let's look at some uniform electric field. Here's E. So when I say uniform, I mean same magnitude, constant magnitude everywhere, constant direction everywhere. Okay, this is a uniform E field. And you move between 2 points. Here's point A, and here is point B. Okay? We have the little displacement vector that points from A to B, so I'm building up some notation and we'll talk about what all this means. Here's a little displacement vector ds between A and B. So ds is that little displacement vector that keeps up with how far I go and in what direction I go. Okay? So moving from A to B, you get a change in the potential, delta V, which is equal to VB minus VA. Okay, oftentimes and most of the time, we want to know potential differences, potential between different points, or the difference between different points. This is equal to, this is the definition of the change in potential. This is the negative of the integral from A to B of E dot ds. Okay? That's how we define it. That negative is there to keep the bookkeeping straight. Okay? You'll see how that works in a minute. We could have done without the negative, and we'd have to keep up with some different stuff, but this negative makes everything work out. How do I say it? Makes it work out where it makes sense. Okay? So you look at the field, how far you went, and the direction. So what's your, remember that dot product? This is dot ds, the dot product between two vectors A dot B is equal to A B cosine theta. Remember that from physics 1. We were talking about work. Okay. So for a uniform field like this, if I have a uniform electric field, that means E is a constant, direction and magnitude. And the angle, as I've drawn it here, it really wouldn't matter the path that I took because it's a uniform field. But the angle between ds and E is 0. I'm moving along, I'm moving parallel to the field. Okay? So the angle between E and ds is 0, cosine 0 is 1. So this just becomes, for the uniform case, the negative of the integral from A to B of E ds. I took care of the dot product. Samantha? Yeah, it's like when we were talking about the gravitational potential energy, because let me leave that up there. Because the gravitational field is a constant, and when thinking locally, it's constant this way in this room. All right. If you move an object from here, an object of mass m, to this point here, and I'm talking about without friction, it doesn't matter the path you take. The only thing that matters is this, not to get too technical with the vectors and everything. The only thing that matters is this difference in height, h. And that's because you're in a conservative system, there are no losses, and that field vector is this way, gravitational field. Doesn't matter if you go here and you go around and then go here. The change in potential energy just depends on the difference in height. And it wouldn't matter in this case. I'm simplifying it just so I can do this integral very simply. It wouldn't matter what path you took from A to B. You go that path. Okay? That path from A to B, the change in potential is what I'm talking about, delta V, would be the same, independent of path. Why would that work? Because when you're here, you're not getting any contribution due to this dot product. Then you're getting a big contribution, then you're taking away some, you're adding some, okay. And in the end, it works out just to be EDS, where DS, which I'll get to, this is, this distance, or the integral of DS becomes this distance between A and B. Just like here, you take this path, and the only thing that really mattered was the distance between where you started and where you ended up along the y-axis. Okay? All right. This case, I took care of the dot product. It's a uniform field. I'm moving parallel to the field. This can come out of the integral because it's a constant. Right? What's the integral from a to b of ds? Well, it's just this distance from a to b. And I'm going to call that distance. I know I called the little vector ds, but I'm going to call that little distance d. Okay? So this is equal to negative ed. A very pessimistic Edward. Why do we need the negative there? If I look at this, VB minus VA, right? That's what I'm saying delta V is. It's the potential at the end point, or where you stopped, minus the potential of where you began. If you move with the field, you're always going down in potential. Okay? And that's the case here. VA is greater than VB. I'm going down in potential. I know this potential thing is sort of nebulous right now, but it's just a word. But it's defined by how you're moving, or the change in potential is defined by how you're moving in the electric field. Okay? So if you're moving with the field lines, you're going down in potential. If you're moving against the field lines, or anti-parallel, as some texts say, anti-parallel means parallel but in the opposite direction. You're going up in potential. All right? So if you go this way, VB is greater than, you swap these two and the negative goes away. Okay? What I want you to remember is, if you're moving with the lines, you're going down in potential. If you're moving against the lines, you're going up. All right? So, it's the same as over here. And I'm going to talk about the difference between this gravitational idea and the electric idea. But if you're moving against the field lines, the gravitational field, you're going up in potential energy. If you're moving with them, you're going down in potential energy. Always. That won't all. Okay, remember I said potential energy. There's going to be a little subtle difference over here when we start talking about electric potential energy. Okay? All right. So if look at, let's just get some numbers and see what kind of potential difference we're talking about. Let's say that the electric field is equal to 10,000 newtons per coulomb. Okay, that means if you were to place a coulomb of charge in the electric field, you would get a 10,000 Newton force. That's not a really huge electric field. Let's let little d equal 50 centimeters. And I'm moving from A to B. So I need the negative here. So delta V is equal to minus ed, which is 1 times 10 to the 4 newtons per coulomb, multiplied by this distance, which is 0.5 meters. And this is equal to negative 5 times 10 to the 3 volts. Because a Newton meter is a joule, and a joule per coulomb is a volt. So about 5,000 volts. Very simple. I'm much more interested in what's happening conceptually than I am these numbers. Okay, all right. So let's talk about this idea of a charge being in this electric field. So I'll draw a new picture. I'm going to have a uniform field. Okay, here's E. Okay. So here's a positive Q at point A, and you move, or you allow it to move to point B. So Q is going in this direction. The change in potential energy of this charge Q, delta U, is equal to Q delta V. That's the idea. The change in the electric potential energy is equal to the charge times the change in potential. Once you've figured out what the change in potential is in this field, then you multiply it by the charge, you get the change in potential energy. This is going down in potential energy, yes? Delta V is negative, okay? And Q is positive, all right? There would be, you can think of it as forces maybe. There's a force in this direction. So this is going down in potential energy and it's gaining kinetic energy. Just like the mass gravitational field system. If you let the object fall, it's going down in potential energy and it's picking up kinetic energy. It's a conservative field, no losses. Okay? Here's what gives us trouble with electric fields and potential energy. We have negative charges. We don't have negative masses, right? We don't have masses that lose potential energy as you go up in the field. But we do here. Because if I place a negative Q in the field, I get a negative bit of Q here. This is negative. You get a positive change in potential energy. You went up in potential energy. Because the force on this negative Q is in this direction, right? There must have been something providing some work to move it this way. Or it had enough kinetic energy that it came in and started slowing down, slowing down, slowing down. Okay? Delta V still gives us this still gives us the correct answer, but we have to pay attention to these negative charges. Okay? However, with the electric potential as we've defined it over here, it's independent of charge. If you're moving with the field, you're going down in potential. If you're moving against the field, you're going up in potential. Potential. Leave off the energy. But then you put a charge in there, you do have to pay attention to that negative or positive. Okay? Positive charges want to move with the field naturally because they're losing potential energy as they move with the field. Just like masses in the gravitational field always want to move with the field. What?
Is it of gravity?
Yeah, gravity. Yeah. They naturally tend to go from high potential to low. You roll something, you push something off a little cliff, it's going to fall. Okay? But with charges, if it's positive, they naturally want to go with the field. If it's negative, they naturally want to go against the field because a negative charge is losing potential energy as it moves this way. Now I've got you all thoroughly confused. This is a lot of bookkeeping, I know, but I don't know any way around it. Okay? All right. If we had negative masses and we all learned, I think from the beginning about the gravitational field and negative masses moving and positive masses, I think this would be like that, but we don't. Okay? Nature decided not to give us negative mass, so. Okay. Questions or anything on this? Do you see this subtle difference between potential and potential energy? Yeah, that potential energy depends on the specific charge. Potential is independent of the charge, really. Depends on the way the electric field is situated. Okay. Here's sort of the payoff of all of this. We're going to calculate the electric potential of a point charge. I'm going to start with a positive charge. I don't have to, but okay, here's a positive charge. So we imagine these electric field lines, or we conceptualize them with these little arrows that are vectors, or field vectors, and they're all radiating out like this. So here's the electric field due to this point charge Q. Here's Q, all right? This has spherical symmetry. I'm drawing a little 2D slice, but you know that it's radiating out spherically, and if we have that little radial vector, I'm going to call it ds in this case because I used ds over there. It could be dr, but ds will work fine. Okay. So ds is that little radial vector that gives me the direction I want to go and that little bit of distance I want to travel. So I'm going to look at the potential difference at this point between 2 points along this ds. This is RA and this is RB. That stands for the radius at A and the radius at B. Wouldn't matter if I was over here moving this way or over here moving this way or over here. We have that nice spherical symmetry. Okay? So by that definition that I wrote down a minute ago, delta V is equal to minus the integral from RA to R, I keep wanting to write just B, to RB of E dot ds. Okay, that's definition. What is the angle between ds and E? Everywhere. I claim it's everywhere. What is the angle between ds and E? Not a difficult question. Zero, yeah. Yeah. ds is this radial vector, okay, or radius vector, and the electric field has this nice spherical symmetry. So the angle between E and ds is 0 everywhere. Cosine 0 is 1. So I can get rid of that little dot. Okay. So this is equal to the integral, or negative the integral from RA to R sub B of E ds. Do you have a question?
Yeah, from that diagram,
Uh-huh.
ds seems like it's acting on this plane.
Okay, you're looking at this.
Yes.
No, these are just a finite representation of an infinite number of field vectors. That field is uniform in a radial sense. It has spherical symmetry. It's everywhere spherically. Any direction I choose that points from the center of the charge outward, I have an electric field vector in that direction.
Including where E is.
Yeah, where ds is. Absolutely.
I'm trying to wrap my head around ds and E having an angle between them of 0.
Okay, well, let's say that I choose this. Let's say that I choose this direction, ds. You're okay with that? Okay. There is an electric field vector here. Okay. That's the same as this one, that's the same as this one, that's the same as this one.
Makes sense.
Yeah. So any ds I choose is going to have that electric field vector along that path. That's spherically symmetric. Okay? All right. Is this a constant? Is the electric field constant as I move from point A or the radius at A to the radius at B? No. The field falls off like 1 over r squared, right? So as I move out away from Q, that electric field is decreasing, decreasing, decreasing. What's the electric field due to a point charge? KQ over r squared, right? Yes, Samantha.
So the only reason it was a constant in the other field is because it doesn't matter where in the field it is, it's going to be that?
The only reason it was a constant in the other case was because I made it that way.
But you can't.
For simplicity, I said, let's just assume a uniform electric field, meaning constant in direction and constant in magnitude.
But it can't be a constant.
No, it's not a constant in this case. This is the only point charge in the universe, and as you move away from it, the field falls off like 1 over r squared. The field's getting smaller and smaller and smaller and smaller as you move away. And the thing is, I can't just pull this E out of the integral. It's not a constant. It depends on S. Since S is my radial vector, then it's going to depend on that distance that I am from the charge. Okay. E, in this case, as I've cooked up these variables, is KQ over S. Let me get, that's a huge Q. KQ over S squared, right? If S is the distance from the charge. Okay. Notation, notation, notation. I'm going to plug this into here, and you get delta V is equal to minus the integral from RA to RB of KQ over S squared ds. But K and Q are constants. I'm going to pull those out. So you get KQ times the integral from RA to RB of negative 1 over S squared ds. So I'm trying to feed you a form, huh?
Your negative,
Yeah, I just put it inside. I'm trying to give you something that you recognize.
I was just making sure that
Yeah, it doesn't matter if it could be out here, it could be over here, it could be down here. Okay. Those negatives can jump around. All right. What's the integral of negative 1 over S squared ds? What do I differentiate to get 1 over S squared? What? No. Yeah, negative 1 over S, right? Yeah. So this is equal to KQ times 1 over S evaluated from RA to RB. Okay. When you do the integral, the negatives cancel, so you just get KQ is 1 over S. So I'm going to write this over here. Delta V. Well, that equals V at RB minus V at RA. Okay, I think in the first class I wrote just B and A, but you get the idea. Okay, and that is equal to KQ times 1 over RB minus 1 over RA. Plug in the upper limit, subtract the lower limit. Okay, well, there's the potential difference between A and B. What I wrote down is the potential of a point charge. So if we can all agree where the zero potential is, then we start doing problems and we talk about these things and we argue and work on point charge distributions. We all can agree where the zero is. Remember when we were doing those problems with gravitational potential energy, I said, doesn't matter where you define your zero because you're always looking at differences in gravitational potential energy and you're working around that zero. This is the same idea. If we can all agree where that zero potential is, then we're all uniform. Okay. Where would you like to make the potential equal to zero? Where do you think a good place would be? Where? Well, what about on the charge? We'll just make the zero right here. Yeah? Big problem. What happens when RA goes to 0? This blows up. The whole thing blows up. What happens to the electric field when R goes to 0? Blows up. It goes infinite. We don't have the tools in this class to handle that. Okay? That's for another day. But there's another place I can think of that we can let the potential go to 0 and everything will be lovely. How about the edge of the universe? Yeah. Infinity, right? That kind of makes sense. If I go out to infinity, the electric field's going to 0 and the potential's going to 0. Getting farther and farther away from the charge, the electric field's decreasing and the potential's decreasing in this case. Okay? That's what we're going to do. We're going to let the potential go to 0 as the radius or the distance goes to infinity. And it doesn't matter which one of these I take to infinity. You'll see in a second. I'm going to let RA go to infinity, okay, and V at RA go to 0. So as RA goes to infinity, that term goes to 0. That's okay. VRA goes to 0. Okay, I'm letting, that's the limiting cases. That's what I'm wanting to happen. So that leaves me with VRB is equal to KQ over RB. All right. Forget the B. It's any point. It doesn't matter where you are. We're letting that potential out at infinity be 0. So the potential due to the point charge, V, is equal to KQ over R. That's it. KQ over R. It's a scalar. It's not a vector. Okay. That is going to make our lives a little bit easier from solving some of these problems. All right. Let's talk about, however, well, let's look at this. I claim that if you're moving with the field, you're going down in potential. If you're moving against the field, you're going up in potential. Does that work for this? Yes. As you move with the field, R is getting larger, this is getting smaller. You're going down in potential. As you come in from infinity and you move against the field, R is getting smaller, this is getting larger. That's what we want. Okay? What about a negative charge? Here's a big fat negative charge. So I know that the field lines for a negative charge look like, or we imagine them being like this. They're little vectors that are pointing inward. They're ending on the negative charge. So for a negative charge, we do have to pay attention to the SIGN, meaning if it's a negative charge, you have a negative potential. Positive charges have positive potentials. Does this still work? So V is equal to negative KQ over R. If you're moving against the field lines, R is getting larger, and this is getting less negative. You're going up in potential. Yeah? So you move with the field lines. R is getting smaller. This is getting larger in a negative sense. So you're going down in potential. Still works. Okay? So we're going to see how to calculate these potentials just like we did with the electric field. We looked at the potential, we looked at the field due to a distribution of charges. We'll look at the potential due to a distribution of charges with everyone agreeing that 0 is out at infinity. Then we'll see how to do continuous distributions of charge based on this idea of the potential due to a point charge. And the nice thing is, no vectors. We just add them up. And then if we can get an expression for the potential due to a collection of charge or a continuous distribution of charges, it's very easy to calculate the electric field based on that potential. Okay, that's it.